and thanks for watching Edupedia World Videos. In this video, we will continue our study of the unit of probability and we'll start the concept of Bayes' theorem. Now, in a previous video, we learned what conditional probability was. So, for example, P of E conditional F was basically the probability that an event in the set E occurs given that, so there is a condition, an event in the set F occurs. So this is conditional probability, which is called PE conditional F, meaning we know that F happens, then given that, what is the probability that E happens? So F is the condition, and the formula we studied in a previous video is P of E intersection F by P of F. Now Bayes' theorem is essentially a way to try to get the reverse condition, meaning if we know PE conditional F, how do we try to get PF conditional E? This is not this obviously, but this is the problem which ultimately led to Bayes' theorem, because people were trying to calculate PF conditional E from PE conditional F. A simple example of this could be, for example, let's say you have two boxes, box 1 and 2. This has, let's say, 4 green balls, 3 red balls. This has 3 green balls and 2 red balls, right? So now we choose one ball at random. We can calculate the probability that the ball is green if we know it's from box 1, that will be 3 by 7. If we know that the ball was from box 2, we can calculate the probability that it will be green, right? So basically we can calculate PE conditional F, where F would be a condition of the form of the ball is pulled box 1, and let's say E is that the ball is green. So this is something we know, PE conditional F. In this case, this will come out to be, given that the ball is pulled from box 1, what is the probability that the ball is green? So we can see this is 3 by 7 because there are 4 by 7 because there are 4 green balls out of a total of 7 balls. So this is PE conditional F. What would PF conditional E be? That would be, given that a ball we pull at random from either box 1 or 2 is green, PF conditional E. So given that it is green, what is the probability that it came from box 1? So first, it's important to understand this problem. In the first case, what happened, essentially we have two boxes full of some balls, green and red, and we choose one ball at random. Then somebody gives us the condition that that ball is pulled from the first box. So that makes the problem easier. Now we can actually calculate the probability of the second condition that the ball is green, 4 by 7. But the inverse case, PF conditional E, would mean that we pull one ball at random from either of the two boxes. We are given the condition that the ball is green. Now the green ball could be pulled from either box 1 or box 2. What is the probability that it is pulled from box 1? Right. So PE conditional F means if the ball is pulled from box 1, what is the probability that the ball is green? PF conditional E means if the ball is green, what is the probability that it was pulled from box 1? And we will try to get PF conditional E in terms of some known functions which would involve things like PE conditional F. So that is the problem we'll try to solve with Bayes' theorem. So let's start. So before getting into the details, we'll look at a few definitions. The first is a property called the partition. Now we know what a sample space is. It is the total set of possible events. So if we look at the simple example we started from in one of the first videos on this topic, we flipped 3 coins in a row, and the sample set S was the total possibilities H, 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 T, H, T, H, T, H, H, and then T, T, H, T, H, T, H, T, T, and T, T, T. So there were a total of 8 elements comprising the total sample space. Now often what is very useful, and it will be useful in Bayes' theorem, is the partitioning of the sample space into separate events. So for example, let's say we were using E and F earlier for events. Now we'll just, for the sake of it, use A, B and C. Let's say A was the set of events H H H, T H T, and T T T. Let's say B was H H T, H T H, and T H H, and let's say C would be what is left? T T H is left, T is gone, and HTT. Yeah, so now, I mean, you could actually write this in terms of words. I don't know exactly what it would be. For example, C could be two tails and one head. Two tails and one head, but the head is not in the middle. So if you wanted to, you could make word problems for each of these. Right now, what I did was just partition these 8 elements into a total of 8 elements. This has 3 elements, this has 3 elements, this has 2 elements, and you'll see that if you take these 3 and 3 and 2 elements, you'll get all these 8 elements. Each and every one of these 8 elements is covered once and only once in one of these. So this would be what is called a proper partitioning of a sample space. So there are certain properties for a partition of a sample space. So a set of events, and now we'll just call them E1, E2, till En. So these are a set of events. In this case, they would be A, B, and C. Is said to be, or is said to represent rather, a partition of the sample space F if, and you have a few conditions. The first one is EI intersection EJ is the null set for all I and j. So in this case, we can see that A intersection B is the null set because they have no elements in common. Similarly, B intersection C is also the null set, and C intersection A is also the null set. So that is satisfied by A, B, and C, that the intersections should be the null set. The other would be E1 union E2 union ... union En should be equal to S. When you take the union of all these elements, all these sets rather, you should get the sample space S. That is true in this case. If you take A union B union C, you'll get these 3 elements, you'll get these 3 elements, you'll get these 2 elements, all of which are distinct. So you'll get these 8 distinct elements. So this indeed is equal to S. So this is true. And the third is sort of a redundant statement. It will almost always be true, but it is that P of EI is greater than 0. Basically, every one of them should have at least one element. None of them should have a non-zero probability. And the reason for that is, in Bayes' theorem, a lot of times PA or PB will come in the denominator, so it will not be valid if that is 0. Right. So these 3 conditions indeed are satisfied. The probability of A is 3 by 8, this is 3 by 8, this is 2 by 8. So A, B, and C represent the partition of this sample space. So basically, essentially what we are doing is, we are breaking this set of 8 events into any forms. We can take this to be the first one, this to be the second one, this to be the third one, and this to be the fourth one. That would also be a partition. You can have any sort of partition as long as these rules are valid. Now keep in mind one thing. Let's say A had one more event which was the same as the event in B. So it has all these events, but along with that, let's say it has H, H, T also. So now it has 4 events. Now even though the union of all 3 of them is still S, because this element is already here, this statement is not satisfied, right? So there will not be a partition space. You cannot have, so let's say you have 10 elements, you cannot take 5 and then you can 4 and then 7 and then 8 and then 6, and as long as every element is included once, that will not form a partition space. You have to partition it properly such that every element comes once and only once in either one of the partition spaces. In that case, the set of events E1, E2 to En would be a partition space. One simple corollary of this will be that if S is the sample space and let's say E is one set of events, then E and E complement will always form a partition, because the intersection of E and E complement is phi and the union of E and E complement will be S. So E and E complement always forms the partition of a sample space. Now let's look at the preceding theorem for Bayes' theorem, from which Bayes' theorem is derived, and this is called the theorem of total probability. So the theorem of total probability and the next Bayes' theorem assumes that we have a proper partition of a sample space. So we assume that E1, E2, till En is a proper partition. And if this is not true, then the theorem is not valid, and the same goes for Bayes' theorem. So what it tells us is that E1, E2, En is a partition of the sample space S, and let's say A is any event associated with S. Then the theorem of total probability says the probability that A will happen is basically the probability that A will happen given that E1 will happen multiplied by the probability that E1 will happen plus the probability that A will happen given that E2 happens into the probability that E2 happens plus ... until you guessed it, probability that A happens given that En happens multiplied by the probability that En happens. So this is a formula you've actually intuitively, I'm sure, used many times. So this formula basically says that if A, the total probability of A happening, means you look at the probability of A happening given that E1 is true, and you multiply it by the probability that E1 is true. This basically gives you the probability that A and E1 are both true. This gives you the probability that A and E2 are both true. This gives you the probability that A and En are both true. And since it is a partition, and always every event will fall in either one of E1, E2 to En. That has to be the case. So let's look at the proper proof of this. We know a few properties of the partition of the sample space. The first is S is equal to E1 union E2 union ... to En. And we also know that EI intersection EJ is the null set for all I and J, which are between 1 and n, and obviously I not equal to j. Right. So what we can do is A can always be written as A intersection S. Since S is a superset of A, the intersection of A with S will simply be A. And so using the upper equation, we'll write it as A intersection E1 union E2 union En. And then we can use the distributive properties, and we can write this as A intersection E1 union A intersection E2 union ... union A intersection En. Now here we'll have to use a little bit of a property which I would like to show to you. So let's say this is the total sample space S, and we divide it into many different portions which would form a proper partition 1, 2, 3, 4, 5, 6, let's say. And then let's say you have an event A which takes this much area. So this would be A intersection E1, this would be A intersection E2, this would be A intersection E3, and so on. Right. Now E1 intersection E2 is phi, means E1 and E2 are disjoint sets. So from this you can see if E1 and E2 are disjoint sets, then A intersection E1 and A intersection E2 are also disjoint sets. E1 and E2 have no elements in common, meaning A intersection E1 and A intersection E2 will also have no elements in common, right? Because A intersection E1 has the elements which are both in A and E1, A intersection E2 is the elements both in A and E2, and there will be no elements which will be in both of them because E1 and E2 are disjoint. So this is the one condition we'll use, that all these are disjoint. And then what we can do is, I'll just rub the upper part, we can use a property which we learned in a previous video. For disjoint sets, probability of A union B is equal to probability of A plus probability of B. Right, we know P of A union B is equal to P of A plus P of B. Actually there is minus P of A intersection B as well, but if A and B are disjoint, then this term is 0. So P A union B is equal to P A plus B, we will use on all of them. So what we get is P of A is equal to the sum of all of these. So P of A intersection E1 plus P of A intersection E2 plus dot 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 plus P of A intersection En. And now we can use a formula, the product formula which we learned in the previous video, which came from conditional probability. We already know that P of A intersection E1, sorry, P of A conditional E1 is equal to P of A intersection E1 by P of E1. So we can multiply here. So this into P of E1 is P A intersection E1. So this basically becomes P of A conditional E1 P E1 plus P of A conditional E2 P E2 plus dot 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 plus P of A conditional En into P of En, which is this final formula, which we have ended up proving. And this is a formula we'll use many times again and again, so I suggest you actually look at the proof seriously and understand how it comes about. Often it will be written in the form of a summation, so what we'll write is P of A is equal to summation of I is equal to 1 to n P of A conditional EI into P of EI. So that is often the theorem on total probability in terms of summations. And now from here we actually try to get conditional probability, the other conditional probability. So what we know is we are given P of A intersection E1. These are the terms that are used here. So now our goal from Bayes' theorem is something which I began this video talking about. We know, let's say, P of A intersection EI, where I could be 1, 2, 3, 4, 5, anything. We would like to find out P of EI conditional A. That means given that A occurred, we would like to know the probability that EI occurred as well. So this is what we would like to find out, and that is the subject of Bayes' theorem. So our goal here is to calculate P of EI conditional A, where I can be any number. Given that we know P of A conditional EI, and we will be using the theorem on total probability here. So this, first of all, we can write it as P of EI intersection A by P of A. Right. Now P of EI intersection A can obviously be written as P of A intersection EI by P of A, and we'll replace the numerator by the same thing we did in the theorem on total probability. So this comes out to be P of A conditional EI into P of EI, and then you have by P of A. This is the multiplication rule which we learned in the previous video. Now we can just simply put in the formula for PA, which we got from the theorem on total probability. So this comes out to be PA conditional EI into P of EI by PA, which we already know, summation. Now I'll use J because I am using here. Sorry, J is equal to 1 to n P of A conditional EJ into P of EJ. This is P of EI conditional A, and this is Bayes' theorem. So now we have accomplished the thing which we wanted to. We have PI conditional A in terms of PA conditional EI. But of course there are a few constraints, we can't do it always. The first constraint is EI has to be a member of a partition of a sample space. So first we'll have to construct a partition of a sample space in which EI is one of the members, and then we can use this formula as long as we know PA conditional EI for all of the members. So before doing a few examples, I just like to go back a little bit to show you something important. So I'm just going to undo this a little bit, because this structure is quite similar to the structure which we had in the previous equation, the theorem on total probability. It's a mistake. I seem to have ran out of undos, so I'll just write it again. The theorem on total probability basically said P of A is equal to P of A conditional EI, P of EI plus dot 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 plus P of A conditional En into P of En. And Bayes' theorem says P of Ei conditional A is equal to P of A conditional Ei into P of Ei by this whole thing basically. So summation of P of A conditional Ei, P of Ei. So this is the theorem on total probability, and this is Bayes' theorem. We've seen proofs of both of them. Now the interesting thing here is, from this we can see P of A conditional Ei, PEI is one of the terms of this total sum, right? It will be somewhere in the middle. And the denominator is the sum of the total terms. So this theorem on total probability has an interesting structure. The first term is basically the relative probability that Ei happens given that A happens. We have to normalize it by adding all of them because the sum does not necessarily need to be 1. But this is relative, this is proportional to PEI conditional A. This term is proportional to PEN conditional A. So that is the important thing. All these terms are proportional, and of course if you add it by the total sum, then you'll make it such that the sum will be 1, which has to be true for probability. Now we'll do a few questions, 2 or 3 questions to try to get a little bit more understanding of these two theorems. But before that, there are a few definitions which sometimes are important in the NCERT papers and the board papers. So I'll just write the definitions and you should try to remember them. Whenever Bayes' theorem is applied, this is only true for Bayes' theorem, which is generally used quite often in probability. The events which were the partition of the sample space E1, E2, En are called the hypothesis. Then P of Ei is called the priori probability, and the conditional probability P of Ei conditional A is called a posteriori probability. Now these terms are not really important for IIT JEE, but for your board exams it might be possible that they might ask you what is the priori probability. So you should know what that is. It is basically just a term for P of Ei. Yeah, let's do a few problems now. So let's start with the type of problem I began this video with. Let's say you have 2 bags, 1 and 2. The first contains 3 reds and 4 black balls, and the other contains 5 red and 6 black balls. One ball is drawn at random from one of the bags and it is found to be red. Find the probability that it was drawn from bag 2. So we know that it is red, so that will be our first event. A, not P of A. A is that the ball is red. Let's say E1 is the event that it is drawn from bag 1, and E2 is the event drawn from bag 2. So obviously these are disjoint events because you cannot draw a ball from both bag 1 and bag 2. And these, when you take the union, form the total set of sample spaces because you obviously will draw a ball from either bag 1 or bag 2. So this is indeed a partition of the sample space. So we can use Bayes' theorem. P of E1 is equal to half and P of E2 is equal to half because we are told that we just choose a bag randomly. And what is P of A conditional E1? That means given that it is taken from 1, what is the probability that the ball is red? That is 3 by 7 because 3 balls out of 7 are red. Similarly, P of A conditional E2 is equal to, and now we have 5 red balls out of a total of 11 balls. So it is 5 by 11. What we need to find out is the probability that it was drawn from bag 2 given that it was red. So we need P of E2 conditional A. Well, we can easily write that this would be P of A conditional E2 into P of E2 divided by P A conditional E1 P E1 plus P A conditional E2 P E2, and everything else is known. This and this and this will basically I'll just cancel because they're all half. So it comes out to be P A conditional E2 5 by 11 by 3 by 7 plus 5 by 11, and if you calculate this it will come out to be 35 by 68. So that is the probability, a little bit more than half, that the ball is drawn from the second bag if we know that the ball is red. And it sort of makes sense because there are more red balls in the second one than there are in the first one. Let's do one more question regarding Bayes' theorem. In a factory we have 3 machines A, B and C which manufacture boards at the rate of 25%, 35% and 40%. So basically of the total boards manufactured, 25% are made by the machine A, 35% by the machine B and 40% by the machine C. And out of their inputs, 5%, 4% and 2% are defective. So we take out a bolt at random and it is found to be defective. What is the probability that it is made by the machine B? So first, A, B and C are basically disjoint events because every bolt will be made from one of the 3 and you cannot have a bolt made from both of them. P of A1 is 25 by 100 or 1 by 4, which I'll just call A as E1, B as E2, C as E3 just for the sake of consistency for notation. P of E2 is equal to 35 by 100, or if you divide by 5, 7 by 20. And P of E3 is equal to 40 by 100, which is 2 by 5. Right. Also, we need the probability, we are told the probability that they are defective given they come from each and every one of them. So let's say there is an event D which is that the board is defective. So what is P of D conditional E1? Given that it is made from the first one, what is the probability that it is defective? 5% or 5 by 100. I'll not cancel this because we'll write all of them in the same terms. P of D conditional E2 is equal to 4 by 100 and P of D conditional E3 is equal to 2 by 100. What we need is P of E2 conditional D. We draw a bolt at random, we see that it is defective. What is the probability that it was made by B? So E2 is the event that the bolt is made by B, D is the event that it is defective. And we can actually calculate what this is exactly. This will come out to be P of D conditional E2 into P of E2 by P of D conditional E1 P E1 plus the second term plus the third term, you know what it is, P of D conditional E3 P of E3. So this comes out to be, now I'll just put in the values, 4 by 100 into P of E2 which is 7 by 20 divided by 5 by 100 into 1 by 4 plus 4 by 100 into 7 by 20 plus 3 by 100, sorry 2 by 100 into P of E3 which is 2 by 5. So first of all we can cancel all the hundreds. So what we are left with is 4 into 7, this cancels with this and gives me 5, 7 by 5 divided by 5 by 4 plus, and again this gives me 7 by 5 and we have 4 by 5. So 11 by 5. And this comes out to be, this is 44 plus 25, so 69, and above we have 28, so 28 by 69 is the probability that a defective bolt chosen at random comes from the machine B. This completes Bayes' theorem. Thank you.